Hello everyone, welcome to today's live stream. Here we have Juraj, and he will talk about the truncated Fock spaces as a way to model second quantization.
Cool.
All right, Juraj.
Sounds good.
Go ahead, share screen.
Okay, so thank you for the introduction. I will share the screen. Okay, so I suppose now you can see my screen.
Yes, we can see it.
Okay. Fine. So, as was already mentioned, hello everybody. My name is Juraj Tkáč, and today I will be sharing my journey on Wolfram Summer School, where I was discovering topic truncated Fock space as a way to model second quantization in Wolfram Language, with the mentorship of Bruno Tenorio and Mats Bahrami. And in the very beginning, I would like to show and somehow explain which kind of topic in terms of science we are moving in. So as you can see, there are a lot of scientific fields.
Could we zoom in a little bit? Maybe, yeah.
Yeah, I can zoom more.
Yeah, sounds good.
Yeah, okay. And we are mainly interested, of course, in terms of physics. So where we are actually in quantum field theory, which means connection with quantum mechanics and special theory of relativity. That's this second quantization, and also term topics which we will be discussing later. And so yeah, we are in quantum field theory. So now I can go back to the main part, and through which I will be moving. It's at first some initialization definitions, then we will go through some proving of that some states are belonging to some class of states. We will be verifying their properties, and in the very end, we will end with some practical stuff, which means get states, which could be then be used for preparation of get qubits, which I will be discussing later. And after that, I will be coming back to initialization definitions because they are so strong and useful, so I will come back to them. So at first, we have there some random complex number generator, which is just basic pseudo-random generator, because we of course don't have, as far as it's known, some great random number generator algorithm, or even some QRNG, some quantum random number generator, still useful. So we are using pseudo-random number generator algorithm, which is already created and prepared in Mathematica. So that's this random real function. Then of course we need some desired norm, because we of course could have a lot of numbers, but we want them to be normalized. So that's why we also considering some norm, which will be also important for the, I would say, theoretical experiment which we've made. So let's see the second definition. It's coherent state. So coherent state, as I have in my introduction, which I can just basically come through. I already mentioned that we are in quantum field theory, and coherent states are a special class of states that could be said are the most classical quantum states that we can obtain. It sounds a bit weird, but we will prove that later. But what does it mean? It's basically that it has a lot of meanings, but one of them could be that we are deriving them by minimizing the uncertainty relations. So it means that we obtain some global minimum. That means we have the most certain quantum states in quantum physics that we can have, because we've gone through that process of minimization of that function, these uncertainty relations. So these are the coherent states that exhibit the classical properties, and that are, for example, for imagination, for those who are not well familiar with them, for example, used in laser physics. So these coherent states would be for us interesting, so that's why we've defined them. Actually, the path to defining them was at first through some pyramidal approach, which wasn't quite useful, because if on these pyramids we would end with coherent state and we want to change some parameters, then we would have to change the whole pyramid scheme. So that's why we finally fine-tuned the code and defined it as a function, as some definition-based structure. So this coherent state is defined by using Wolfram Quantum Framework, function quantum state, and then table of some coefficients with factorials, which actually are Poisson coefficients. So it means that these coefficients exhibit Poisson distribution, which we can then later see in the graphs. What is also important are creation and annihilation operators, which I have in the third definition. These operators simply describe something, again, for those who are not, they are watching someone who is not well familiar with physics, basically processes when new particles are appearing or disappearing from our desired environment. Because, as I've said, and what was also said, we are working in terms of second quantization, which means we are coming from particles to fields. That's the point of second quantization, that we come from first quantization of particles to the fields. And in fields, particles can appear and disappear, be created or annihilated. And the fourth definition is the desired Fock state. Again, the name of the topic is Fock space, and it's second quantization in Wolfram language. So what is that Fock state? In quantum physics, we have, of course, as is well known, we are operating in terms of Hilbert space. But if we want to restrict it, so we would be said truncate that Hilbert space, we obtain a Fock space. And in Fock space, we have some finite dimensional vectors which describe our states, and with which we can operate more easily than with infinite dimensional vectors. This is our fourth definition, and with these four definitions, we can simply build the whole framework which we are going to use. So these were initialization definitions, and then if we go through some introduction, as I've said, something about coherent state, as there could be seen. These are the Poisson coefficients. And as could be seen, that coherent state could be defined by multiple mathematical operations, he said, because there are either these Fock states, these vectors with n, or vacuum states on which are applied displacement operators. Displacement operators are interesting operators in terms of quantum optics that are shifting our states from vacuum states in this example for coherent states to higher states. And this displacement operator we will be discussing more later, because we are also defined it and verified its properties. So at first,
can I ask a couple of questions quickly?
Yeah.
So I'm just trying to like grab onto a little bit of understanding here, because it's quite mathematical. So can you maybe just start with explaining what a Fock state is, and then what is this representing here, basically? Like, just give us like a high level motivation for the exploration a little bit.
Okay, so the motivation is to use some finite dimensional states, for example, which could be even practical or even theoretically more handful to operate with, because, for example, if we will be going towards the qubits, because that's the main motivation of this topic, then we would need some finite dimensional states, for example, in terms of qubits, some finite dimensional resonator state, which could encode two-level system, which is simply qubits like two levels. And in theoretical sense, back to the question, Fock states are simply finite dimensional Hilbert vectors, would be said like that.
Okay.
So, and
that's the
also
idea, using these
notation. Yeah, and also the notation, because again, coherent states are denoted like these bracket form with alphas, and usually the Fock states are denoted by by number notation in this bracket form. That's why there is this bracket with n, because it's simply, for example, for 5-dimensional coherent state, we should obtain sum of elements with these exponents, these Poisson coefficients, and vectors with 0, 1, 2, 3, 4.
Okay.
So this is the notation. So let's say we are operating with 20-dimensional Fock space. So we define it by this n, as we are using the initialization definitions. Then we want to use the creation and annihilation operators to define them in order to handle the processes like emitting photons and such. And then if we use this, we can define the desired Fock state, which means that 15 state from this 20-dimensional vector space. These were just some, I would say, manipulations for like preparing the stuff for further experiments. We've tried to apply annihilation operator to our desired state. We normalized it. We then tried to apply the amplitudes and then compared whether the amplitudes are same or not, or which the norm is, whether it's normalized or not. And it indeed was. And as we went further, then what is important, again, for these who are watching and are not familiar with quantum physics that much, we wanted to use Hamiltonian, which is the most important operator, which describes the evolution, because we don't really want to operate with states which are just stationary and nothing is happening. We wanted to see how these states are evolving and what is happening. So we've defined at first number operator, which is operator which is including the total amount of particles, in that sense photons. Then we've defined Hamiltonian by this number operator, which is consisting from annihilation and creation operator, and applied it on the desired state. In this Wolfram Quantum Framework, it could be then, of course, more described for what it includes. So, and after that, if we are able to do this, then we can simply experiment with any state we want, with any desired state. But we will be continuing with these 20-dimensional. It was just randomly chosen example. And what we will want to see is whether, as I've already mentioned, the behavior of probability distribution is respecting probabilistic distribution in terms of Poisson curve. So we've prepared the desired states. Again, we've used the initialization definitions, normalized them in order to obtain total probability equal to 1, that particles are not somehow moving out from that space, or that probability is not respecting some, I would say, normal behavior. So after that, we can see that the fit is indeed Poisson. So we've plotted it and see for all of the states that it respects the Poisson behavior. Then we've compared it for different alphas, because we want to see the different complex numbers, that is not only respecting behavior for one alpha. So that was the first outcome.
So was that to be expected, or was that kind of remarkable that it's so directly?
That was actually expected. We've just proved that it really respects the Poisson behavior as the structure, mathematical structure of these states is containing the Poisson series, Poisson coefficients. And so if we are done with that, we are coming to the displacement operator. So the displacement operator, as I've been mentioned, is great in terms of quantum optics and in terms of shifting the vacuum states and preserving their minimum uncertainty, because it still preserves the great properties of vacuum states. It just means that if we are in phase space, what is important to mention, that is being used to describe how the state is behaving, because of course in classical mechanics, we are also in phase space. In quantum physics, we are in Hilbert space mostly, or Fock space in our case. But for these almost classical states, we can use this optical phase space. So these pictures I don't have in my notebook, but the desired properties are visualized like that, like some bulks or some elliptic curves in phase space to handle the uncertainty which is still occurring because we are still in quantum world. But back to what we were discussing and what we were exploring was the definition of the displacement operator, because that quantum framework is well prepared for a lot of different ways how to handle with a lot of mathematics in terms of definitions. In this example, we can define this quantum operator function with either matrix exponential of some matrix, or we can define quantum operator exponential of quantum operator. And then we can measure what is more efficient in terms of CPU time. Is that absolute timing function? And as we can see, the first case is a lot more efficient. And if we compare it, we just simply subtract them, we obtain that it's the same result, it's the same entity. So if we have defined these displacement operators, we can simply take one of these definitions and now verify the coherent state, because as we know, it's some displacement of vacuum state, and what we also know is the minimum of uncertainty relations. But what we also know was another approach, I think originally, which was, I'm not sure whether it was Schrödinger, but I think so, who derived it also as the eigenvalue for annihilation operator. So we simply prepared the displaced vacuum. So we prepared the displaced vacuum function, just applied it in pure state. Then we've listed the amplitudes and compared it by normalized coherent state, and see that there is no difference. So it's the same. So displaced vacuum applied on zero state, on vacuum state, so displacement operator on vacuum state, minus the normalized coherent states and its amplitudes is simply the same. So we verified it, and it means it's working properly as we wanted. So now back to the quantum evolution, because we've already prepared the desired Hamiltonian, including the number operator. I will come back to it, how the form of Hamiltonian is looking. And by that, we do some evolution. We want to see how these states are behaving, what is happening with them. So again, we have these 20-dimensional Fock vector, Fock state, and these simply, by this definition, create evolution at first in step one step in one time unit, which could be considered a second. And then we apply more time steps and see the resolution and final result. And that was the main result of this discovery and this research, that if we apply mean position on this evolved process, that we simply measure where is the position of this state, which is evolving and changing, we can see this nice classical sinusoidal curve. And this is pretty similar to the curve or sinusoid of the classical electrical field. So that's also the reason why we call these states the most classical quantum states. Because this position of that field is oscillating sinusoidally as the position of the field in electromagnetism in classical sense. So after that, we were also able to do some symbolic evolution, because this framework is not only working for concrete values, but also for symbolic.
Well, so wait, what's oscillating sinusoidally? Is it a position or a momentum vector, or is it sort of like a spin state or a phase?
It's a position vector.
Okay.
Because we apply position operator. So that's this step. So at first we apply the evolution, then position operator. So all of these evolved steps we transform to the positions, because as we are handling with operators in quantum physics, every operator is corresponding to some property, or how I understand it, mainly in terms of position operator or momentum operator, that if we apply on our desired state, then it shows the position or momentum with some probability or in some process. So in that case, we can see some oscillations.
The momentum operator is also gonna oscillate, right? If you measure the momentum observable in a similar way.
Yeah.
Is it gonna be like a phase shifted? Is it easy to just construct it now?
You mean constructed in what sense?
No, the same
Really?
kind of graph, but not the position, but the momentum one. So
Yeah.
just
It should hold also for momentum.
no, but can we construct it now? I mean, just to see how it looks like, whether there's like a phase difference between them.
Yeah. So I should take a look on precise definition of momentum operator. Now I'm not.
It's just about like
Mentioned.
changing the sign between annihilation and creation operators, right?
Okay. So
Instead of a plus, it's just a minus.
yeah, you mean in that step?
Yeah, I think so.
Yeah.
If I remember correctly.
Okay, so it's evaluating.
It's, yeah, it's not the most efficient way to compute the expectation value. Yeah, let's wait it out. Oh, it's essentially 0, right? Does it make sense? So that we essentially have a classical particle in the sense that we are localizing the momentum. We know its velocity, right?
Yeah.
That's kind of. Hold on a minute.
Actually, if we can fully localize momentum, it doesn't really be like that because we don't really have the fully classical state. We still have some uncertainty.
Yeah, but it's essentially 0, right? It's mostly maybe it's a numerical noise. So this graph is just 0. Is it correct or not? I'm just trying to understand. It's maybe we're not computing the observable correctly. With the
I
later
think
lab.
it should exhibit the same.
Maybe there's some imaginary.
Yes.
You should
Yeah.
multiply it by imaginary.
Yeah, I think it should be a bit modified because it wasn't, as I bit remember, in the precise definition of momentum operator, it wasn't only with the sign, but maybe also with some another term.
Maybe you should divide it by I. Something
Yeah,
like that.
maybe.
Multiply it. Doesn't much that no difference too much. Right. No, not pi. The I, the imaginary
Okay.
unit, capital case. Otherwise, it's not the same I. Yeah, make the capital I.
So it's not working. I think it was.
It was working. Just type the capital I. Why doesn't it work? Yes, that's it.
Actually, in that case, yeah. So,
Yeah. Oh, so there is a phase difference.
Yeah.
Should it? So yeah.
Okay. Okay, so it still means that there are these oscillations, and it's behaving like almost like classical field. So then what was the last but not least part was the symbolic evolution, because we wanted to verify the known result that it remains coherent even if we change the amplitude or if the amplitude is changing. So as we applied it, then we compared it with our predefined coherent state, and with these some beta random with some complex exponential. And then when we compared it, it was the same. So it was in terms of evolutions, and finally we got to the, I would say, most important part, and most interesting one, which are the get states. So maybe you know there is one company in France, it's not the advertisement, but it's called Alice and Bob, which is handling with interesting technology called get qubit technology. It's based on these coherent states. They have special class of states called get states, which are simple superposition of two differently oriented coherent states. And like this, as you can see, if you measure the probabilities, you are jumping by 2 photons. It's actually easy to explain because we are superposing 2 states. So if we want to go up to higher occupied states, we need to add 2 photons for each of the states. And there is another definition. We don't really have to go by the plus sign, but also by minus sign, and we then obtain jumping by
and then C again.
This one.
The one that you're adding into the definition, you add NNCA variable.
Yeah, it's not normalized coherent state.
Okay. Essentially the same one without the minus, right?
Same one, yeah. This is with plus.
I mean without the minus alpha. It's the same state as coherent state, and then what?
Yeah.
Plus alpha. Yeah. Okay.
And there we are again jumping by 2, but now with odd Fock vector notations. And in the future, what is the further approach, or what could be then used by this also Wolfram Quantum Framework, is some analysis of desired qubits based on these get states, which can be created from them, and to see their evolution, their control of how they are behaving, because these are the nowadays applied technologies in France, and which are still gaining a lot of interest in quantum computing community. And they are still based on these coherent states and this Fock space properties. So if we can just come back to our initialization definitions, we just obtain almost all important stuff from just these functions, which could be further modified for purpose and need, which is desired for any researcher who will need it. So simply then for the qubits, then it could be modified for specific experiments and stuff. So this would be the main part by me, and thank you for your attention.
Thank you.
Yeah, that was cool.
We
Any
have
other
a
questions?
we have a Bruno, your mentor, working on it actually. So there's some functionality about second quantization coming up in the framework. Is in a more designed way. So all of the alienation operators and even phase space plots, all of those Wigner functions, Husimi functions, all this kind of nice plots of quantum states and truncated Fock space states gonna be also implemented. It's gonna be nice.
Yeah, perfect. He mentioned something, but not that much.
Yep.
He was like,
Awesome. Cool. Dugan, any other questions?
I just had one question on some of the plots. Were there complex plots being displayed for the quantum states? This little inset, like right here, this pure state. It's in the iconized little things, and there's a square. Usually it's red, but sometimes it's rainbow colored.
Yeah.
Like right here.
For example, here.
Yeah. So are those complex value plots?
Yeah.
Okay, so that's the color is the phase, and then the lightness or darkness is the absolute value.
I would say it like that more the colorful it is, more complex and
yeah. This is just essentially like a complex array plot of a density matrix.
Right. Okay, that's what I was thinking it was. Good to have that validation. All right, that's all I had. Thank you, Juraj. That's very interesting stuff.
Thank you for
it looks
opportunity.
Yeah, thanks, Juraj. That was very interesting. I appreciate your time on that. Great. Okay, thanks everyone for tuning in. Hopefully you guys learned some stuff about quantum, and if it was above your head, then I hope you were entertained. And yeah, we'll catch you on the next stream.
Right.
Yeah.
Bye-bye.
Okay.
Bye.
Bye.